Good morning to all of you. I am Rama Krishna from KL University, delivering lectures on heat transfer. Today we are going to take up the forced convection in internal flow manner. What the student will be able to understand at the end of this session: what is an internal flow? What do you mean by hydraulic mean diameter? And how to find average velocity in a pipe flow? How to find average temperature in a pipe flow? How to identify whether the flow is laminar or turbulent in case of internal flow? And how to determine the heat transfer coefficient in laminar flow? And what is the importance of Dieter's-Boyle correlation? And how do you estimate the heat transfer coefficient in turbulent flow? To start with, let us see what is an internal flow. In the last class we have seen external flow, that is flow over the plate, flow over the cylinders and flow over the spheres. Now we will consider the flow of a fluid through a pipe, as shown in this figure. Water is flowing through the circular pipe, or a fluid is passing through a rectangular duct. So in case of internal flow, how to estimate the heat transfer coefficient, we are going to witness in this session. The flow through pipes and ducts of various cross sections is known as internal flow. Most of the industrial applications, the pipes are made up of circular cross section only, because they can withstand large pressure differences without undergoing any distortion. So when we use a pipe, normally circular pipe, the diameter we will consider for assessment of different non-dimensional numbers. But when we take up a non-circular cross section like a rectangular duct or square duct or triangular duct or hexagon duct, we will see later those geometries. Then how to calculate the Nusselt number and Reynolds number? Under such circumstances, we have to consider the equivalent diameter as the hydraulic mean diameter equal to 4 times the cross-sectional area of the pipe divided by its wetted perimeter. And the Reynolds number is always calculated for internal flow using rho v diameter by mu. If it is non-cross-sectional, non-circular cross-section, this diameter d will be replaced by hydraulic mean diameter. And further we know that the mass flow rate of fluid through a pipe is equal to rho into area into velocity. So therefore, when you multiply both numerator and denominator with A, the rho AV becomes m, and in the denominator A is pi by 4 d square. So that 4 comes to the numerator, d square and d cancels, you will get pi d. So the other formula to determine Reynolds number in internal flow, when mass flow rate is given, is 4m by pi d mu. Directly you can use this without going for velocity calculation. Another advantage, that's all. But most famous equation, as you are aware, it is V d by mu, or rho v d by mu is the Reynolds number. Another important thing which you have to remember in internal flow is the critical Reynolds number is 2300. In the external flow it is 5 into 10 power 5, but whereas in internal flow it is only 2300. So if the Reynolds number is less than 2300, the flow through the pipe or through the duct becomes laminar. If the Reynolds number is greater than 2300, it is turbulent. Most of the students confuse here. They consider Reynolds number 2300 as critical value even for external flow also. It's not so. Only for internal flow, the Reynolds number critical value is 2300. For external flow, it is 5 into 10 power 5. Now when I say hydraulic diameter is 4 times cross-sectional area by wetted perimeter, for different cross sections, how to calculate this hydraulic mean diameter? Let us consider the circular tube, the beginning itself. 4 times cross-sectional area pi by 4 d square divided by pi d. So which is nothing but diameter. In case of a square duct having sides A and A, the hydraulic mean diameter is 4 times A square by perimeter, wetted perimeter 4A. So it is A. For a rectangular duct, it is 4 times cross-sectional area AB by perimeter 2 times A plus B. So it becomes 2AB by A plus B. Like external flow, in internal flow also, the boundary development will happen. Both velocity boundary development and thermal boundary layer development. Imagine fluid is flowing through a pipe like this. At the beginning, the velocity is 0 on the surface, but here it enters into with a velocity of v. So as we proceed along the length of the pipe, you can see the boundary develops like this, just like in plate, and at this point, any point on the boundary, the velocity of the fluid is equal to v, and at the wall the velocity is 0. So because it is a circular pipe, throughout the pipe, when you look in this view, in a three-dimensional way, this boundary develops and it envelops, and thereby you will get in this shape. The perception is, imagine this is one plate and that is another one plate. So boundary layer development of a plate is like this, and for the top plate it is like this. Imagine infinite number of plates are surrounding one another, one over the other. The pipe boundary layer development you can understand. Now if you take a point like this, the velocity is here v, here is v, here is v, and here on the boundary is also v. But from the boundary to the wall, it reduces from v to 0. Similarly here v to 0. So this is the profile. But as we move, you can see that the point where the velocity attains equal to that of free stream velocity rises up. So the velocity profile here is almost at the entrance, it is a rectangle. Just now slightly blunt, and then a rectangle, and then a curve. But here the rectangle portion is only a low one, very low, and the remaining is a curved one. And at this point, the velocity at the center is maximum, and it reaches to 0 at the wall, and here to 0. And in case of laminar flow, the shape of this profile that develops is paraboloidal profile. And once you leave this point, the velocity profile at any point in the pipe remains same. There won't be any change. So this is another important observation. As we move in the x direction along the length of the pipe, the velocity profile gradually changes and then it becomes constant. That distance up to which there is a variation in velocity profile is known as entrance length, or more technically hydrodynamic entrance region. Beyond this hydrodynamic entrance region, the boundary is fully developed, and then we say the flow is a fully developed flow, hydrodynamically fully developed region. If you consider in this case the rate of change of velocity, where velocity is a function of both radius and x, with respect to x is 0, because see, in the fully developed region the velocity at any point, the length remains same, it won't change. So it is independent of x but varies only in radial direction. So in a fully developed region, dou v by dou x equal to 0, and hence velocity is only a function of radius. Just like hydrodynamic boundary layer is developed when fluid is passing through the pipe, you will have thermal boundary layer development also. It is something like this. Fluid is flowing through this. The temperature here is Ts, surface temperature, but fluid temperature is T alpha, will attain after certain depth, and throughout this region it continues to be T alpha. So like a velocity boundary layer, a thermal boundary layer is also developed, and the temperature is said to be fully developed only after certain length, and that is called thermal entrance length. So missing here, thermal entrance length or thermal entrance region. And the flow from here onwards, where the temperature profile remains same, is called thermally fully developed region. And in this case, if you consider the variation of temperature, the surface temperature as a function of x, and temperature which is a function of both radius and x initially considered, and this is Ts and T mean, the derivative of this will become 0 because it will not change, always it remains the same in the fully developed region. Now if you observe this figure, the velocity is gradually changing. The velocity is 0 at the wall, increasing and reaches a maximum value, and then again reaching 0. So to determine the Reynolds number in this, you have to use the formula rho v d by mu. Which velocity I have to consider? So I have to find the average velocity of fluid or mean velocity. Imagine this is the actual velocity profile. In case of laminar flow, I told you it is a paraboloidal shape, and in case of turbulent flow it is in slightly blunt shape. But anyhow, the velocity here is 0, and at the center line of the pipe it is V maximum. So therefore, I will idealize this as a rectangle, a circular ring. So the flow through this and the flow through this should be same. The flow through this is rho AV, rho into cross-sectional area of the pipe into average velocity. And the flow through this is, take an elemental strip and elemental area dA. So rho into V into dA, integrating between the limits AC, 0 to AC. Now if you closely look at it, Vm equal to integral AC rho V dAc by rho AC, and this dA is nothing but the area through which the fluid enters into it, which is considered as 2 pi r dr, circumferential area of the ring into a thickness of dr. That is the element, fluid element entering at any radius r with a velocity v. So if you integrate between 0 to r, you will get rho v 2 pi r dr by rho, and this area is pi r square. Rho cancels, and we will get average velocity of fluid flowing through the pipe is 2 by r square integral 0 to r v, which is a function of r comma x into r dr. Similarly, because the temperature is also varying, and what should be the average temperature or mean temperature? So this is the actual temperature profile while fluid is flowing. The minimum temperature, hot surface we are assuming, Ts is greater than T alpha. So you have maximum here and minimum at the center, and then it reaches maximum. And it is idealized as a rectangular shape like this. So the energy entering into this is mCp m. Assuming that the energy at 0 degrees centigrade is 0, you can write mCp m, which is equal to, for this one, take an elemental strip of delta m passing through it, mCp t, that is delta m Cpt. Integrate it again between mass flow rate, total mass flow rate m to 0. And this delta m mass that enters into that elemental strip can be written as rho AV. So rho into velocity at that point into area of cross section dA, elemental area. So therefore the Tm equal to integral Cp T delta m by mCp, and this delta m is rho AV, rho into V into area is elemental ring area of thickness dr, 2 pi r dr. To understand that elemental ring area 2 pi r dr, you better imagine the side view of this. At a radius r, dr thickness, ring is considered through which fluid is flowing, and at that particular radius r, the velocity is v. The side view, if you imagine, you can very easily understand this concept. So rho into average velocity into pi r square into Cp. This is for mass flow rate in the idealized case. So again cancels, you will get 2 by average velocity into r square, 0 to r, temperature as a function of r comma x and V as a function of r comma x, r dr. This is how you have to find the average temperature or average velocity in this case. In laminar flow, it is observed that the maximum velocity is equal to 2 times average velocity. That can be easily proved. So another important thing is, in a thermally fully developed region, the derivative of temperature difference at any point with respect to the surface temperature, Ts minus T by Ts minus Tm, average value, with respect to x is 0, because the profile remains constant throughout the pipe, and hence it won't vary with respect to x, and it is 0. Thus this ratio is independent of x. Then the derivative of this with respect to r must be independent of x. That is expressed like this. Dou by dou r of Ts minus T by Ts minus Tm is equal to minus this Ts minus T is nothing but dou T by dou r at r equal to r by Ts minus Tm is not a function of x, because along the length of the tube, once the flow is fully developed, the temperature profile will not change. The velocity profile will not change in the fully developed region. Similarly, the temperature profile also will not change. The rate of heat flux is given by the convective heat transfer coefficient at that location, Hx into Ts minus Tm, can also be written as K dou T by dou R at R. So you can evaluate the local heat transfer coefficient in that length Hx as K dou T by dou R at R equal to R by Ts minus Tm. Because this dou T by dou R at R equal to R is not a function of X and Ts minus Tm is not a function of X, in a thermally fully developed region, the local convection coefficient is constant. Hx is not depending on X. H value remains same. Therefore, both friction, which is related to wall shear stress, and convection coefficient H remains constant all along the length of the pipe in a fully developed region of tube. Very important. See, the Reynolds number is calculated using the formula, Vd by nu. No length term is involved in this. So in the beginning itself, Vd by nu, if the Vd by nu value is more than 2300, right from the entrance tube to the exit of the tube, the Reynolds number remains same, the Vd by nu value, and the flow is fully turbulent right from beginning to the end. Suppose the Reynolds number is less than 2300 Vd by nu, and however be the, or whatever be the length of the pipe, throughout its flow, the flow remains to be laminar only. Unlike in plate flow, after some time the flow turns into turbulent, will never happen because it is independent of length. So the Reynolds number is constant throughout the length of the pipe. The heat transfer remains constant throughout the length of the pipe. The heat transfer coefficient and the friction factor also remains same throughout the length of the pipe. This is very important inference which you have to remember. Now let us quickly have a look at the entrance length. This is how the boundaries are developed. If Prandtl number is greater than 1, the velocity boundary layer is shorter and thermal boundary layer will be more. That means the entrance length. This is thermal boundary layer and this is the velocity boundary layer. And afterwards the flow is called fully developed flow. The heat transfer coefficient, you can see up to the fully developed region they drop because the thickness of the boundary layer goes on increases. Even friction coefficient also. But once the developed flow is fully developed one, in this region the H value or F value completely remains constant. The entrance length for laminar flow is given by the formula 0.05 times Reynolds number into diameter of the tube. And the thermal entrance length in the laminar flow is multiply with the Prandtl number. Prandtl number into lambda. So that is the reason why when Prandtl number is greater than 1, thermal entrance length is greater than hydrodynamic entrance length. You can see here thermal entrance length up to this, hydrodynamic entrance length up to this only. So it is more. In case of turbulent flow, both thermal entrance length and hydrodynamic boundary entrance length will remain almost equal and varies from 10 to 20 d. Generally they take it as 10 times d. Could be even 20 d also. It may vary from 10 to 20 d. We cannot exactly predict that, where the development of flow becomes full, a fully developed flow will establish. Another important aspect in the pipe flow is sometimes by using energy balance equation, you can determine the convective heat transfer coefficient. Take a pipe into which the mass flow rate of fluid entering is m dot with an inlet temperature Ti and exit temperature Te. Energy is supplied to the pipe from outside, heat is supplied, so temperature increases. So the heat gained by the fluid is mCp T exit temperature minus T inlet. The heat gained by this fluid is nothing but due to convective heat transfer from the wall to the fluid. So it can be considered as convective heat transfer coefficient at the pipe H, the surface area, assuming this length is L and diameter is D, pi dl, surface temperature Ts, minus Ti at the beginning and Te at the end. It varies. So therefore we will take the average temperature. H pi dl Ts minus Te plus Ti by 2. And this equation you can use for any constant wall temperature condition. And using this equation, any one unknown parameter, maybe length or the exit temperature, if you know the value of H, can be determined. Instead of constant wall temperature, if you take a constant heat flux condition, equation slightly differs. So imagine there is a pipe which is supplied with constant heat flux. Inlet temperature of the fluid is Ti, exit temperature is Te because it absorbs heat from the outside, so the fluid temperature increases. Heat flux is supplied continuously same, so therefore as the fluid flows, at the inlet the fluid temperature is low, so more heat will be taken up by the fluid. As it proceeds, the temperature of the fluid increases, so it takes less and less amount of heat, therefore wall temperature increases. So in a constant heat flux region condition, the surface temperature is not constant, it increases as X increases. And the average temperature is Te plus Ti by 2, you can estimate. And this is the delta T. So you can write the equation, total heat entering into the pipe is equal to heat flux at the surface into surface area of the pipe, pi dl, which is again equal to mCp exit temperature minus inlet temperature of the fluid. So therefore the exit temperature of the fluid is equal to inlet temperature plus Q dot SAS by mCp. Just rewritten the equation. And we know Q dot S is equal to HA into the H into Ts minus average temperature. So Ts is Tm plus Q dot S by H. So if you take any suction like this at a point where the temperature is a Tm, after elemental thickness of dx the temperature is Tm plus dTm, energy entering is mCp dt Tm and leaving is mCp Tm plus dTm, and the heat that is supplied into that elemental strip is dq is H into Ts minus mean temperature Tm into dA. Let us equate now these two. The mCp dTm, that is net energy leaving, is equal to net energy supplied carried by the fluid is mCp dt. Q dot S into area. Area is perimeter into dx. So from this we can immediately say dTm by dx is equal to Q dot Sp by m dot Cp. Heat flux is constant, perimeter is constant, mass flow rate is constant, Cp is constant, therefore it is constant. Therefore the slope of temperature, average temperature with reference to x, if you draw, it is a constant. dTm by dx remains constant. And this dTm by dx is equal to dTs by Ts, because whatever is the change in this, same change will occur in the surface temperature also. And if you take the partial derivative of the wall temperature and temperature of the fluid at any point to that of Ts minus Tm, like in this boundary development, and because this is constant and not varying, the derivative of it with respect to x becomes 0. Or in other words, 1 by Ts minus Tm into dou Ts by dou x minus dou T by dou x is equal to 0, which indicates that dou T by dou x is equal to dou Ts by dou x. So temperature of the fluid at any point, variation with respect to x and the surface temperature with respect to x, they are same. So dou T by dou x is equal to dTs by dx equal to dTm by dx equal to q dot sp by m dot cp is constant. Hence, for a fully developed flow which is subjected to constant heat flux, the temperature gradient is independent of x. Thus, the shape of the temperature profile do not change along the length of the tube. That is what already we have seen. Whether it is a velocity boundary layer or thermal boundary layer, the profile shape will remain same. The temperature profile shape will remain same. Now coming to this, a circular tube subjected to constant heat flux, the perimeter is 2 pi r, so therefore mass flow rate is rho Vm into cross sectional area pi r square, and dou T by dou x etc. is, we have seen, 2qx by rho Vm Cp r is the constant value. When fluid is flowing through a pipe or a duct, because of the friction between the fluid and the pipe surface, there will be always some amount of pressure drop. So that pressure drop in a laminar flow is determined by using the formula delta P equal to FL rho V square by 2D, where this rho V square by 2 is known as dynamic pressure, and this F is known as Darcy constant or Darcy-Weisbach friction factor, equal to 8 times tau dou by rho Vm square, where Vm is the average velocity. Fluid mechanics flow through pipes chapter, if you remember, you can very easily recall that the head loss due to friction, Hf is equal to FLV square by 2ZD. The same formula we are using but in different units, FL rho V square by 2D. So for a circular tube under laminar condition, the friction factor F is 64 by Re. Same tube under turbulent condition, the F value is 0.79 logarithm of Re minus 1.64 to the power minus 2. That is 1 by square. This is the friction factor for laminar and this is for turbulent, and total pressure drop is given by the formula FL rho V square by 2D. If it is not a smooth pipe, if it is a rough pipe, to determine the value of F, you have to use the chart developed by the scientist Moody, which is called Moody's chart. The x-axis on this chart is Reynolds number and the y-axis is surface roughness epsilon by d. So when it is epsilon by d, if you know the value of roughness and diameter of the pipe, you can choose that curve corresponding to Reynolds number. You can go to the y-axis and determine the value of F. You can clearly visualize here, for a smooth pipe, it is only one line. Nothing depends on this, only Reynolds number. And for rough pipes, for each one, the curve varies. And if it is fully turbulent flow, this equation, this curve you can use. And transition region, you can see here roughly at 2 into 10 cube, 2000, 2300, roughly at that point it is shown Below this it is laminar flow, and beyond that it is turbulent flow, and this region is transition region. The equivalent roughness for new pipes from Moody and Colebrook data they have prepared. Different types of pipe materials and the relative roughnesses are shown here. And he has developed an equation for rough surfaces to determine the friction factor. 1 by root F is equal to minus 2 log epsilon by D by 3.7 plus 2.51 by RE square root of F. A little bit complicated, that is why better we use the equation. Different materials, the roughness in millimeters or in feet, in foot is determined as per this equation. Because even internal flow is also a forced convective flow, in this case also Nusselt number is a function of both Reynolds number and Prandtl number. And we have seen already through Prandtl, in case of turbulent flow, the thermal boundary layer thickness and hydrodynamic boundary layer thickness will become same, or the momentum diffusivity and thermal diffusivity are becoming same. In other words, there is a relationship between heat transfer and the momentum transfer. That analogy between momentum and heat transfer is done initially by Reynolds and slightly modified afterwards by Colburn. This is very important from examination point of view. Let us have a look at Reynolds analogy, or the same analogy we can take up even in external flow also. Since we have missed it there, let us see how to apply this analogy between momentum and heat transfer in internal flow. When fluid is flowing inside the tubes under turbulent condition, in addition to its momentum diffusivity nu, because of the turbulent set-in, it will also have eddy diffusivity of momentum. So the equation tau is equal to mu dou u by dou y or nu rho du by dy. In the place of nu, in addition to that momentum diffusivity, we add the eddy diffusivity of momentum. And the expression is written as tau by rho is equal to nu plus epsilon m du by dy. Similarly, the equation for heat transfer is heat flux Q equal to minus K dt by dy. That K can be expressed as alpha into rho Cp. So therefore Q by rho Cp is alpha dt by dy, where alpha is thermal diffusivity. In addition to this thermal diffusivity, in case of turbulence, due to this eddy diffusivity of momentum, eddy diffusivity of heat also arises. So therefore, Q by rho Cp, by adding this eddy diffusivity, can as minus alpha plus epsilon h dt by dy. And if we assume Prandtl number is 1, eddy diffusivity of momentum and eddy diffusivity of heat will become same, and by dividing these two equations one with the other, you will get Q by Cp tau du is equal to minus dt. Now let us integrate it, the du varying from 0 to average velocity Vm, and dt is varying from surface temperature to bulk fluid temperature. So Q by Cp tau integral du equal to minus dt. So Q Vm by Cp tau is equal to Ts minus Tb, or Q, and we know Q equal to H into Ts minus Tb. So therefore, from this equation I can write tau is equal to delta P into area pi by 4 d square by pi dl, which is equal to delta P into diameter by 4L, where delta P is FLV square rho by d. So therefore, tau can be expressed as this f by 8 rho v square, f by 8 rho v square. Hence, we can say that the Stanton number, which is nothing but the ratio of Nusselt number by Reynolds number into Prandtl number, is equal to f by 8. This tau by rho Vm square becomes the ratio of Nusselt number by Reynolds number into Prandtl number. The h by rho Cp Vm, this h by rho Cp Vm is nothing but Nu by Re Pr, which is equal to f by 8. That is called the, so you can say the Stanton number is equal to f by 8 is the Reynolds analogy. This analogy we can apply only when the Prandtl number of the fluid is 1. So what it indicates is, if you know the friction factor, you can determine the convective transfer coefficient. So it establishes a relationship between convective transfer coefficient and friction factor. If the Prandtl number is not equal to 1, then Colburn has modified it as a Stanton number into Prandtl number to the power 2 by 3 equal to f by 8. This analogy is called Colburn analogy. I repeat, Stanton number means it is the ratio of Nusselt number divided by Reynolds number and Prandtl number. The product of Reynolds number and Prandtl number is known as Peclet number. Different non-dimensional numbers, that's all. And the ratio of Nu by RePr is called Stanton number. So the analogy between momentum and heat transfer says the Stanton number into Prandtl number to the power 2 by 3 is f by 8. So if you substitute the formula for f, etc., etc., you will get again Nusselt number as a function of Reynolds number and Prandtl number with the different coefficients. Now let us come back to our internal flow problems. If it is a laminar flow and constant surface temperature is maintained, this is the velocity profile that it will develop, and the friction factor is given by the formula 64 by Re. And the Nusselt number under such condition is 3.66. Why it is given as a constant Nu equal to 3.66? Because when I take the Reynolds number Vd by mu for internal flow, mu value generally in the order of 10 power minus 6. So therefore Reynolds number will be always greater than 2300 and the flow is in general turbulent flow. If the Reynolds number is very low, that is laminar, then less than 2300 is possible only when the fluid is having high viscosity. So in that small range of values, the Nusselt number does not change much. So they have considered for constant surface temperature Nusselt number as 3.66. We can derive this also, of course, because it is only an undergraduate course. I am not taking up the solution of different boundary layer equations. In advanced heat transfer, we will see how to solve these equations and how to develop mathematical models and how to design a thermal system, etc. Anyhow, if it is laminar flow instead of constant surface temperature, this is constant heat flux. If constant heat flux is maintained, Under constant heat flux condition, the Nusselt number is considered as 4.36. So it implies that the rate of heat transfer will be more in constant heat flux condition when compared to constant surface temperature condition. This value 3.66 and 4.36 are only for a circular geometry like pipe. If it is of other cross sections like rectangle, ellipse or triangle, what is the value of Nusselt number? You can see here. And Reynolds number is calculated using average velocity into hydraulic mean diameter by mu. And hydraulic mean diameter means 4 times cross sectional area by perimeter. And Nusselt number is HD, hydraulic mean diameter by K. The equation for Nusselt number is constant value depending upon A, B values, ellipse. For example, A by B is 8, constant wall temperature condition, Nusselt number is 3.72. Then directly you apply HDH by K equal to 3.72 and then take the hydraulic mean diameter, calculate for this K value, you calculate the value of H. Then Q equal to HA delta T we can apply. That is the advantage of having this table to readily assess what is the heat transfer coefficient and what is the Nusselt number for various cross sections. In addition to this, several scientists have developed, particularly in the entrance region, because the heat transfer coefficient is not constant. Edwards et al. They have developed Nusselt number as 3.66 plus 0.065 d by L REPR plus 1 plus 0.04 d by L REPR to the power 2 by 3, etc. Similarly, Sider and A equation is more famous equation. And Edwards et al. For thermal entry region also he has average Nusselt number between two isothermal parallel plates when flow is there, how to determine the Nusselt number he has done. So depending upon the problem and its nature, we have to pick up these equations and solve. And for turbulent flow in tubes, that is when Reynolds number is greater than 2300, as we have seen, if it is a smooth tube, F is equal to 0.79 log RE minus 1.64 to the power minus 2, where Reynolds number ranges from 10 power 4 to 10 power 6. And equation for Nusselt number is 0.125 F REPR to the power 1 by 3, and this is called Colburn equation. 0.125 is nothing but F by 8. And Nu by REPR is nothing but Stanton number. And you have one more Prandtl number. So Stanton number into Prandtl number to the 2 by 3 is 0.125 F by 8. This is nothing but Colburn analogy. It's a very simple equation. If you remember, Stanton number into Prandtl number to the power 2 by 3 equal to F by 8. You can solve the convective heat transfer coefficient problems very easily for internal flow. That is the importance of analogy. And this equation, Nusselt number equal to 0.023 RE to the power 0.8 to the power into Prandtl number to the power 1 by 3. The range value of Prandtl number and validity for Reynolds number is given. More famously, in most of the designs of heat exchangers or pipes, they use this Dittus-Boelter correlation, which is Nusselt number equal to 0.023 Reynolds number to the power 0.8 Prandtl number to the power n. And n you have to take 0.4 if the fluid is getting heated up. And you have to consider n equal to 0.3 if the flowing fluid is getting cooled. So this is the relation to determine the convective heat transfer coefficient under turbulent condition inside the tubes or pipes. For laminar flow, you need not assess, directly the values are given in the table. And for turbulent flow, the most famous equation is Dittus-Boelter correlation. So if you remember this equation, it is very easy for you to design any heat exchanger. You can determine the convective transfer coefficients, etc. inside the pipe and outside, etc. Outside when it is in annulus flow, etc. Most important thing we have to remember in this internal flow problems is fluid enters at inlet temperature Ti and leaves at Te. So while it is flowing through the tube, gradually its temperature is increasing. So at which temperature I have to consider the properties to evaluate the Reynolds number or Prandtl number. So that temperature is the average bulk fluid temperature or bulk mean temperature. That bulk mean temperature is defined as the average of inlet temperature plus exit temperature of the fluid. So TB is equal to Ti plus Te by 2. So if you take this equation TB equal Ti plus Te by 2, calculate the bulk fluid temperature, and at this bulk fluid temperature extract the properties, use Dittus-Boiler correlation, you will get the value of Nusselt number. Because of the simplicity in this equation and the error involved in this also being less relatively, most of the times people use this Dittus-Boiler correlation for first level understanding of design concepts in heat exchangers. There are several other equations proposed with a little more accuracy, and all these equations again the properties are to be evaluated at bulk mean temperature. And for liquid metals having Prandtl number in between 0.04 to 0.1 under constant wall condition and under constant heat flux condition, two equations are proposed by Schleicher and Rose. So again in this the Prandtl number is to be evaluated at the surface temperature, not at the bulk fluid temperature. So depending, as I said earlier, from case to case you have to keep a data book with you or the table containing all these equations. So to suit to your application, depending on the range of Prandtl number and Reynolds number, the exact equation you have to pick up and solve for Nusselt number and the convective transfer coefficient. That will give you more or less accurately the convective transfer coefficient under that condition. Another important application in the internal flow is flow through annulus. Suppose you have two pipes, one inner pipe and one outer pipe, and the fluid flows through this annulus. So in that case also you have to consider the hydraulic mean diameter to calculate the Reynolds number and the Nusselt number. The hydraulic mean diameter is given by 4 times cross-sectional area by wetted perimeter. The cross-sectional area of this annulus is pi by 4 d naught square minus di square, and the wetted perimeter is pi into d naught plus di into 4 times. So 4 cancels, pi cancels, and you will get d naught minus di. So the difference in diameters of outer pipe and inner pipe will become the hydraulic mean diameter. Based on this only you have to calculate Nusselt number and Reynolds number. A simple table is given for different values of di by do, the Nusselt number and etc. for a given case. Of course it is not specific. So this is the theoretical part of internal flow. So we have seen till now what is an internal flow. The fluid flowing through pipes or through ducts is called internal flow. It is also of two types, laminar or turbulent, depends on the Reynolds number. The critical Reynolds number is 2300. If it is more than 2300 it is turbulent. If it is less than 2300 it is laminar. And Reynolds number throughout the pipe remains same, so there is no question of a laminar flow converting into turbulent, etc. In the beginning, if the Reynolds number is greater than 2300, it is throughout turbulent. In the beginning, if it is less than 2300, it is throughout laminar. While fluid is flowing through the pipes, we have to determine the friction. That's a Weisbach relation we will use, delta P 4FL rho V square by 2D, where F is the friction factor, and in laminar conditions F is equal to 64 by Re, and in turbulent condition the F equation is given separately for smooth pipes and for rough pipes. And in case of rough pipes, instead of going for a calculation, you can also use the chart developed by the Moody. Is a simple thing. So with the help of that F, you can determine the friction, and then due to that friction coefficient, the head loss due to friction and power loss for pumping the fluid, you can determine. This is more or less related to a fluid mechanics problem in flow through pipes. Like in external flow, even in internal flow also there will be hydrodynamic boundary layer and thermal boundary layer. The hydrodynamic boundary layer and thermal boundary layer development we have seen, and only after that certain length only the velocity profile or temperature profile remains. Cut length up to which there is a variation in velocity or temperature profile is called entrance length. In this entrance length, the H value, friction factor, temperatures, velocities, everything will vary. And once the flow is fully developed, all are constants. So the analysis of heat transfer in the entrance region is a little bit complicated. So most of the times we assume that the flow is fully developed and calculate the heat transfer coefficients. For laminar flow, Nusselt number is a constant. It is 3.46 for constant wall temperature and 4.6 something for constant heat flux. And for turbulent flow, we use that retest boiler correlation. Nusselt number is 0.023, Reynolds number to the power 0.8, Prandtl number to the power n. Where n is equal to 0.3 if the fluid is getting cooled and 0.4 if the fluid is getting heated up. So this is how we have to analyze the internal flow convection problems. Let us go to some numerical examples to identify how we can apply